So that cliff I was talking about, we followed it along here, and now it's coming down to the trail level. Look at the log right there.
Oh yeah. Oh my goodness.
Right there. Yeah, right in the middle of that convoluted bedding.
This is massive, Kurt.
Yes.
I mean, it's just hard to imagine
and
this
it
thing
continues
sliding
on
down.
from here. So it's been half a mile that we've followed it here. It continues on for another 3/4 of a mile. Imagine this whole cliff is not in place. It's slid down from above, and the same cliff goes up the other side. So the whole thing slid down into this valley. It indicates a time when this valley was cut out very rapidly, much more rapidly than any process we're familiar with in the present.
That's all post-flood here, all these
This would
events.
be the Arphaxadian Epoch
Arphaxadian.
stuff. It's similar to the present, just bigger.
Yeah.
Okay, and we see boulders in the present eroding off of cliffs.
But
not
this
this
is just-
scale. Not
it's
this scale.
massive.
This is huge. So we're looking at that Arphaxadian Epoch when we kind of imagine in your mind that boulder sliding down the hillside.
But the rocks themselves are pointing to something, to the epoch before that, to the
Right,
flood.
exactly.
Is
The rocks that have actually slid down show evidence in them of a time before that.
that right? Yeah. So what are we seeing then in the rocks?
Well, this is a really cool place. This is a kill zone. During the time that this rock was being formed, this would not be a place that any organism could survive. This was complete destruction. This is catastrophism on a magnificent scale. About halfway up this cliff here, you can see kind of a blotchy pattern.
Oh, yeah.
You got layers
Right.
above and layers below,
Right.
but a blotchy pattern in between. It's about 6 feet thick. That's actually what we call a seismite. When you've got soft sediment that an earthquake shock wave runs through, it deforms that sediment. And in fact, it settles the sediment down, causes water to come out, which deforms it, and that's called a seismite. It's made by seismic or earthquake activity. This is 6 feet thick. Now, you're probably not familiar with seismites to know how incredible that is. We can produce seismites in the laboratory, or I can go to the edge of a ocean or a lake in that wet zone of the sand along the shore and stand there. Now you gotta make sure no one's looking to see this, but you stand there and you vibrate. And if you vibrate, you'll notice that when you do, the sand will almost liquefy. Water comes out of the sand and runs down to the water. Now if you look closely, what's happening is you're vibrating the sand, it's occupying less volume, and it's pushing the water out from what was between the sand grains, and it's escaping and then flowing down. Now, if you look closely, you'll see that the water comes up in little tiny volcanoes here and there, kind of bubbles up. And if, again, you gotta make sure no one's looking, and you go down there and cut into the sand in the middle of one of those little volcanoes, you're gonna see the layers of sand going down the beach. But in that place where the volcano is, they're bent upwards. The water has left the sand and come out of the sand, creating what we call a fluid evulsion structure. Now, in your incredible power on the edge of a body of water, you can produce fluid evulsion structures that are about 1/8 of an inch high, something like 1/4 inch. Earthquakes are bigger. They can create bigger structures, and bigger the earthquake, the bigger the structures. So a decent earthquake that is shaking buildings produces 1 inch or so of fluid evulsion structure.
Only 1 inch of a seismite?
Yeah. Now the biggest earthquakes that we've witnessed in the last 50, 60 years since seismometers have been developed produce 11 inches. The big Anchorage, Alaska earthquake of 1964, 8.2, something like that on the Richter scale, monster earthquake, produced about 11 inches of convolutions or seismites.
Okay.
Yeah, exactly. And as near as I can tell, when you double the thickness of your convolutions, your seismite, it requires an earthquake about 16 or so times bigger. This thing's 6 feet. So it's 6 times
beyond
the
imagination.
thickness of the biggest earthquakes we're familiar with in the present. So we're talking about a time with earthquakes that are unimaginable.
Right.
Huge earthquakes. Probably no process on the present Earth is capable of doing that. And so we have a period of huge earthquakes, but that's not all. Because for that seismite to work, you've got to have deposited that 6 feet of sand very quickly, full of water, still full of water to create that. And so we got 6 feet of sand deposited very rapidly, then hit by that earthquake. So we've got evidence of very rapid deposition, very deep deposition, and you can see here at one layer we've got what we call cross beds. The layers cross up into, you've got a bed of a certain thickness. There's one there, it's beautiful, it's about a foot thick or so. And the beds within that bed cross it. These are called cross beds. So if water is moving and carrying sand, it carries sand in and deposits the sand down the front face of a dune.
It's like we saw in the Grand Canyon.
Yes, you would have seen some very large cross beds there. And that's indicating that moving water is carrying sand grains and depositing this. So it's not just depositing sand very quickly, it's depositing sand in moving water, and all these cross beds face in one direction. They're all going that way. In fact, not just here, but everywhere this unit is found, you've got cross beds that are moving from the east to the west. And this thing is found from Alabama to the south to Pennsylvania in the north. This thing goes across the entire north-south cross-section of the United States, indicating a time when water is moving across the continent, probably about 1,000 feet above present sea level, moving ocean across the continent, carrying sand, depositing it very rapidly, depositing it in moving water, and simultaneously being hit by earthquakes, enormous earthquakes.
So what we have, I mean, right here in just this small area, we have the clear evidence that this was deposited rapidly, and that there are these cataclysmic earthquakes that are beyond our imagination that are all happening while all this is still wet.
And there's more, because there's a lens of material here that starts thin over on this side and thin at this side, and it gets thick in between. It's a lens-shaped structure. That's a segment of this sand that while it was being deposited, while it was still soft, it slid down. So the whole area is apparently being uplifted, upended, and stuff is sliding down as it's being deposited. So we not only have rapid deposition, but we also have this whole area being uplifted. Well, what's to the east here? What's the source of the uplift? Not but a few dozen miles to the east, we have the Appalachian Mountains. So while this is being deposited, the Appalachian Mountains are being raised upward very rapidly. Water is going over the top of the mountains, ripping the tops of the mountains off and carrying the debris into this area, depositing the sand, and carrying the sand across the continent. We can trace this wedge of sediment, which is thickest at the Appalachians, thinning to the west, past the Mississippi River. We've actually found sand grains from the Smokies in the Grand Canyon on the other side of the continent.
That's
There's a time when water was being moved across entire continents, depositing layers of sediment hundreds of feet thick. You've seen it in the Grand Canyon.
Yes.
Those great layers.
Huge.
Okay, you're just seeing a part of it, 200 miles of it. That's just 200 miles of it. It carries across the entire continent.
Yeah, that gives you the sense of how massive all of this is.
It's incomprehensible. Underneath this unit, remember this unit doesn't belong here, it belongs up above. So if you look at the rocks that are in place here, one of these rocks is one that I used to do some caving in. That caving is done in a cross-bedded oolitic pentramites containing dolomite.
Well, sure.
You don't have to know what that means. It's just a very specific description of a very specific rock. There's tens of thousands of feet of sediment of rock layers in Tennessee. There's only one, it's a few hundred feet thick, that is a cross-bedded oolitic pentramites containing dolomite. That same unit is on the other side of the continent as well. It's in the Grand Canyon. There's a cross-bedded oolitic pentramites containing dolomite in the Grand Canyon that has caves in it. It's known as the Red Wall.
Oh, yeah.
About halfway down.
Sure,
about
yeah.
halfway down the canyon.
Yeah.
That's the same unit. It's the same lithology, same rock type. Up in Montana, it exists also at tens of thousands of feet. There's one cross-bedded oolitic Pentramites containing dolomite. It's got caves in it. Cave of the Winds, for example, in Colorado
That's
Springs.
exactly right.
You're
Yeah.
familiar with
Been
that?
there, I
That's
have been.
in that same unit.
Huh.
You can trace the unit across the entire continent. And so and contained in it are little critters that come from the ocean that have been ripped off of wherever they lived, like coral pieces. Beautiful coral fossils in this. They've been carried, broken from where they live, because coral has to be sitting on a solid surface. If it's sitting in the mud, it sinks into the mud and the little guy dies. Okay, so it's got to be on a solid surface. But we find these coral pieces, beautifully preserved, sitting in what? Mud. We see them sitting in carbonate mud. They can't have lived there. They were only dumped there. So these are living organisms ripped off of some source thousands of miles away, carried across the continent and dumped in places like here and across the continent. So we're talking about a continent-wide scale event that is depositing thick layers of sediment across huge distances, 1,000+ feet above sea level, being carried thousands of miles from where it came from into place, while enormous earthquakes are going on that are the kinds of things you might expect with asteroids hitting the Earth or something, and mountains are being raised very quickly at the same time. That's the flood.
This is part of what Peter is referring to as the earth being destroyed at that time. So we have the evidence here of the tumultuous moment, but when you talk about little pieces of the coral and so forth, those are pointing back then to the Ante-Diluvian period.
Exactly.
And it tells us what was there. What do we see in the rocks here that help us understand more about what that world was like?
Yeah, if we go a little bit further down the same trail, we'll see some of that.
All right, okay.
Let's go on
Let's
down.
do that.
So here we're continuing. That same cliff is now below the trail. It's coming down, and it's coming down towards the river here, towards the creek. And this is where it comes down to the creek and then goes up the other side. And underneath this overhang, we had some cool things to look at. As a matter of fact, right there, see that structure right there? That's a fossil log.
Well, you can even see the bark ridges.
Yep, the impression of the bark. You can see that right there. It's an even bigger one up there with the curvature.
Sure do.
Curvature of the log. So we've got a number of logs in this particular sandstone unit.
So what is this telling us, Kurt? What are we seeing here?
Well, first of all, we've got evidence in this rock of flowing water. You see this little pebble here?
Right.
That's a quartz pebble. See that extends? It's about 3/4 of an inch in diameter. There's several in here that are 3/4 to an inch in diameter. And a pebble this size, for water to move it, the water has to be moving at a pretty good clip.
Yeah.
Probably moving at about 1 to 2 meters per second. It's moving from the east to the west. The water velocity apparently to carry this size pebble is what's necessary to carry 2-foot diameter logs.
Yeah.
So we have evidence of moving water, which we saw already with the cross bedding and all that sort of thing, but here we have further evidence in the things it's carrying.
Yeah. So more indications that all of this was just not laid down over a long period of time with very slow processes, but what we're seeing here is something was laid down again rapidly under some tumultuous kinds of conditions.
And it can't be deposited slowly. You just can't move water slowly and deposit pebbles this
those things
size.
would be sinking to the bottom.
That's right. You can't even roll them along the bottom with water moving that slowly. So these are entire units. I mean, everything you can see. You're talking about tens of feet of sediment being deposited at a time. Steve Austin talks about the nautiloid bed, for example, that a 6-foot thick unit being deposited very quickly, basically moving at maybe 200 miles an hour, moving into place and settling in place. Huge masses of sediment moving very rapidly. That's really the best way to explain this kind of thing.
All that makes sense.
So we have evidence of the catastrophism of the flood, but also it's carrying evidence of the world that existed before the flood. That world that then was, being overflowed with water, perished.
Right.
Well, here's an insight into that world. We're seeing logs from forests before the flood. Think about the world's forests. You got forests in the tropics, you got forests in North America.
Yes.
The world's forest. Now, bring a flood on the world, destroy the entire world. You're going to bury some of those trees immediately. But what about the rest of the trees? Floating on top of the waters following the flood must have been trillions of trees.
Huge mass of
Huge mass of trees. We see in Mount St. Helens, for example, right after the eruption of Mount St. Helens, that collapse of the mountain went into Spirit Lake, pushed all the water of Spirit Lake out of the lake, and the water went up 900 feet up the side of the hills around it, swept all of the soil and trees from the sides of those hills, came back into what is now Spirit Lake. At the end of that eruption, there were about 1 million logs floating on that lake. And over the years, they've gotten waterlogged and sank down to the bottom of the lake. But there's still 250,000 logs.
They're still floating there.
It's been 35 years. Now, if you still have logs floating after 35 years from a small thing like that with only 1 million logs, how many logs do you think are floating around on the world's oceans during the flood?
Yes.
And here's some of those logs. So
And especially in that world before the flood, that Ante-Diluvian world, which could have been even more lush than what we have today.
could well be. In fact, going down the path a little bit further, we can see more information which tells us, yes, there's good reason to believe that it was a even more lush world than today, more trees than today, and a little bit different. If we look at these logs, kind of hard to tell from this location, but they're different kinds of trees than we have in the present.
What kind of trees are
Well,
they?
these turn out to be what are called lycopods. In the present world, we have scrawny little lycopods. We have herbaceous lycopods, soft, short plants, not tall trees. But these are arborescent lycopods. These are lycopods that grew to the size of trees. So they're in that group of plants known as lycopods, but they're unlike anything in the present. And what's really interesting about them is that they're hollow. They're logs that actually don't have secondary wood in the inside. Like the trees you have around here, you cut into them, you're going to find hardwood in the middle.
Right, yeah.
You cut into these, you will not find hardwood in the middle. All you're seeing is the bark, the impression the bark made in the sand. There was nothing in the middle. In fact, some of them are full of sand because there was nothing aside from the bark. And so this is that's a weird kind of tree.
It is.
A tree that has no central core with wood in it. What's going on there?
So why would a tree have no inside?
Yeah, that's an interesting question. And when we look more carefully at this, we realize we have more parts than just the bark. We find also branches. Branches are also hollow. And we find, well, you would call them roots, but technically they're not roots. They're called rhizoids. But those are also hollow. And the rootlets coming off of the roots are hollow. This is a weird kind of plant. A whole tree that's hollow in every aspect, in its branches, in its stem, in its roots, in its rootlets.
Okay, there must be a reason for that.
Yeah, I think so. In fact, the rootlets are so soft, and can you imagine a root that's hollow making its way through soil? Could it do that?
I doubt
It's
it.
going to collapse.
Yeah.
So something's odd about this. Now, it turns out in the modern world, we do have some plants that are hollow, with hollow roots and hollow rootlets coming off of them. Now, they're all little plants. They're not trees. But every one of them are plants that live in water. They float on water. So there's air in the inside of the trunk and the roots that allows the plant to float. That's part of what gave me the idea, and actually Joachim Scheven back in the early 80s, he's from Germany, got the idea that maybe these trees are actually floating. That rather than their roots going through soil, their roots intertwine with the roots of adjacent trees. The trees are light enough to float, and you have a floating forest in the pre-flood world. Since they're all bark and they float, once they're floating, once you've destroyed the forest, once they're floating logs, because these are horizontal, they're apparently floating in water to get down to this point. While they're floating, and let's say while they're still floating on top of the water, they rub against one another and peel their bark off. Now, once the bark's gone, they're gone, but the bark can then filter down to the bottom of the body of water and accumulate as a pile of bark. And that big log mat can be blown around by the wind and deposit that bark over a large area. And if that was the case, you would expect that perhaps those layers of bark landed on a flat surface, built up on that flat surface. When the log mat blew away, the flat surface would end and other sediment would come on top, and you'd end up with a layer of bark that had a flat bottom surface, a flat top surface. When that bark is then coalified, you'd have a layer of coal. A very special kind of coal that's made of bark. And in fact, if we go down the trail, we can see some of that coal.
So you would expect that if we have trees that were floating, we'd expect to find a coal bed here somewhere.
Yes,
and
we can do that. So if we follow me, we can go back and we can take a look at one of those coal seams.
After you.